All right, let's go ahead. Let's start by reviewing a little bit of the new material from yesterday. Your final is on Monday, and I did make it 9 o'clock. So it's going to be next door. Okay, lithium aluminum hydride, what is this? It's a reducing agent, so it's going to add hydrogen. Okay, and what will it turn a carboxylic acid into? A primary alcohol. Yeah, so it's almost just like making that. So you see we have 1, 2, 3, 4 carbons. So you draw 1, 2, 3, 4 carbons, alcohol. It's not technically what happens in the mechanism, but for the predicted product's sake, it's just like taking that off. Okay, then we also looked at this. Okay, what would happen here? Yeah, it'll pull the alcohol off. So instead of putting the alcohol right there, we're going to put the carbon chain, which is how many carbons? 3. 1, 2, 3. So 1, 2, 3. Yep, which makes a ketone. Then our final one, and let's go ahead and do the mechanism for this one. This is SOCl2. What does SOCl2 do if you're just predicting the product right now? Yeah, so instead of the alcohol there, you will have chlorine. Which is the acid chloride. So on this one here, the mechanism starts off, it's almost like I have 2 carbonyls. So then you have to figure out what's the most nucleophilic thing on here, and it's going to be this alcohol. And we had a whole chapter where alcohols are nucleophiles. So this is going to attack this carbonyl here. Yeah, which forces them up, back down, kicks off chlorine. So let's see what we just did there. Chlorine left. And now I have S, and you see the electrons went back down, so double bond, and that chlorine is still there. So this S double bond O Cl group just makes this alcohol into a good leaving group. Okay, it's stabilized by resonance. You see with this double bond here. Oxygen now has a positive charge. And remember, anytime an electronegative has a positive charge, it wants to gain those electrons back. So it wants to break that bond there. So what will attack the carbonyl? The chlorine. It's going to make a bond there, which will cause the electrons to go up, come back down, and what will kick off? The oxygen. So be sure to know that mechanism. Okay, so that's all the new stuff we learned from chapter 20. Then we went into chapter 21 and we started with the inner conversions. So let's go over the hierarchy, or let's go over the naming first. Which one ends in OL chloride? The one with the halogen is the acid chloride. Acid chloride ends in OL chloride. What about amide? Which one ends in amide? What about oic anhydride? Anhydride. O8. Ester. Well, I feel like I'm missing one. What is a cyclic ester? Lactone. A cyclic amide? Lactam. I remember like amide. I don't know if that helps. I think that's all of them. Is that correct? Let's see. Yeah. So that's all your naming. And now the inner conversion. So what is the hierarchy? What's the most reactive? Acid chloride. Then anhydride. Then ester. The amide. Carboxylic acid. So remember, this is the order, and they can only make what's below it. And then if I want to go and make this one, what can make it? The carboxylic acid with, what did you say? SOCl2. So we practice with these. If I want to make an anhydride, what do I put over the arrow? Yeah. So let's say I start with this acid chloride. And I want to make that. Carboxylic acid. So do you see that this side looks like this side? Okay. So this is what I'm adding right here, replacing the chlorine. So I put HO and then the carbonyl, which is your carboxylic acid. And what if I want to make the amide? Let's say I want to make this. Then what's the new part? The new part's this right here. So I put N, CH3, 2, and then what do I always add? H. What about the ester here? Be HOCH3. And then let me go up. I'm running out of room. The carboxylic acid. Water. And this is for all of these. So if I started off with an ester, now an ester can only make amide and carboxylic acid, okay? But if I start with an ester, if I want to make an amide, I put an amine in there, just like I did down here. If I start with an ester and I want to make carboxylic acid, I still put in water. So what goes over the middle here doesn't change, okay? An anhydride, you always need to put a carboxylic acid. And an ester, you always need to put an alcohol. All right, let's look at one of these mechanisms. Let's look at the anhydride. So let's do. Well, let's just put NH2 in there, or NH3 in this case. Okay, so what happens first here? Nitrogen, it doesn't matter which carbonyl. Well, let's just put the final one. Let's say we do this one. Okay, we're making that one. So it's going to attack this first carbonyl here, which will cause those electrons to go up. Okay. Now, what would our leaving group be? The carboxylic acid. So if I push these electrons back down, this will leave, but what will it want to grab? A hydrogen from right here. So that is the mechanism for all of the interconversion reactions. The only difference is that, I could have a different leaving group. So if I had an acid chloride, what would be the leaving group? The chlorine, yeah. And when it grabbed a hydrogen, it would be the HCl. I'll show you. Notice the final product is the same. Okay. Now, just like I did over here, what does the nitrogen want to attack? The carbonyl. Electrons go up. Okay. Then what do? Electrons come down and kick off what? Chlorine, which will grab hydrogen. So do you see that the exact same mechanism? It's just a different leaving group, which doesn't matter because it's just leaving, right? Well, it does form this intermediate here, so you will want to stop and. Yeah, that one does happen like that. Okay, so let's practice these. Let's do some synthesis. How would I go from here to here? Strong oxidizing agent. Do you see I'm adding more oxygen bonds? So you're going to oxidize it. So I'm going to use the Na2Cr2O7. Then here, I went from carboxylic acid to acid chloride. How do I do that? Yeah. SOCl2. And let's say I want to, let me add this up. I want to then make the anhydride for the carboxylic acid. And which side, the left side or the right side? The right, over here. So I already have this side, right? So that's what I'm adding on there. Could this reaction successfully take place? No, why not? Yeah, this is more reactive than the amide, so this will not take place. So remember the hierarchy of things. We have acid chloride, anhydride, ester, amide, and carbacid. I'm abbreviating these, obviously. So our amide is right here. Do you see that ester is above it? You cannot make anything above your rank. Okay, only below. So this reaction, we're trying to go from amide to ester, which would be from here up, could not occur. Could the reverse reaction happen if I put in NH3 and go backwards? Yes, because at that point then I'm starting at an ester and I'm making an amide, and I can always go down. So see where what your starting material is, and then look on your chart. Are you going up to make it or down to make it? And what's the only way you can go? Down. And so on the final exam, you might, like as soon as you get the exam, if you want, just write this down on the back or something. Okay, so then you don't have to sit there and spend any of your time worrying about the order of this or anything like that. It'll be on your exam written, then you can leave your mind so you can focus on other things. Okay, so just write this down. You can abbreviate it like this because I'm not going to grade you on your scratch paper or whatever. So write this down so that you understand it, however you want to abbreviate it, and then remember it that way. So there's a few other reactions that undergo in this chapter, and we've already seen a lot of these before. So the acid chloride, because it is the most reactive, has the most additional reactions. So if I put in my acid chloride, let me go ahead and just write the rest of them down. Oh, terbutyl. That. It's OT bute. Okay. Lithium aluminum hydride, is it strong or weak? Strong. And what does it add? Hydrogens. How many times can it react? Twice. So if I had a carboxylic acid and I put lithium aluminum hydride in there, I think it was the first reaction we did today. What happened? Primary alcohol. The same thing happens to a acid chloride. So just look on here. How many carbons do I have? 2. Draw your 2 carbons. 1, 2. And then draw your alcohol. It will turn carboxylic acids and acid chlorides into a primary alcohol. Where does the OH come from? Or the oxygen, I should say? From this oxygen right here. So here's where this will turn into OH. And then what's my leaving group? Yeah, the chlorine. What about lithium aluminum hydride, but it only has 1 hydride? Yeah, so if it only reacts 1 time, do you see that there's only 1 hydrogen there instead of 4? Okay, so this one, when it reacts 1 time, just replaces chlorine and hydrogen. So 2 times, the strong one, goes to the primary alcohol. It adds 2 hidden hydrogens. This one only reacts 1 time and adds 1 hidden hydrogen, right? Because if I had another hydrogen come in and it attacked right there, what happens to those electrons? They go up, and I can go ahead and have it grab an acid if I want. And then what did I just make? That one. So that's the difference. This one, if I have another hydrogen come in, it will create that one. But since I only have 1, it stops right here. Okay, what is this? Grignard, and how many did I show there? So how many times do you think this will react? Twice. So what am I adding onto there? 2 CH3s. What's my leaving group on acid chloride? HCl, right? So is that going to be in my final product, like my organic product, I should say? No. So I'm going to add my 2 carbon groups. So I have right here 1, 2 to start with, right? Now I add another carbon group, which would be I'm going to put it as CH3. And then another one coming up there as a CH3. And what does the carbonyl become? Alcohol. So lithium aluminum hydride and Grignard, do you see, are similar. This one adds 2 hydrogens and creates the alcohol. This one has 2 carbon groups and creates the alcohol. Oh, this is here. This floating up in the air is nothing. What about copper lithium? Is that as strong as Grignard? How many carbon groups does it add? 1. So what is it similar to? The second one, the 1 hydride. But instead of adding a hydrogen, what am I going to add? CH3. So you see here, these are the same. So instead of putting a hydrogen there, because I have the hydride, I'm going to put the carbon there. and they both end up with the carbonyl, right? So you add your nucleophile, keep the carbonyl. These, add your nucleophile, carbonyl goes to alcohol. Yeah, so let's say I had a butyl chain coming off of here, then the butyl chain would be added here. Anhydride is not very reactive towards these. This is just through experimentation. So if you wonder why, it's for whatever reason, it doesn't work very well with these. But ester does. But is ester as reactive as acid chloride? No. So it's only reactive towards the strongest ones, which would be your full lithium aluminum hydride and your Grignard, the ones that react 2 times. So if I put an ester on here, and let's see, let's put lithium aluminum hydride in one reaction and then Grignard in the other. I'll go ahead, I'll make this carbon chain longer. Okay, lithium aluminum hydride will react how many times? Twice. So when I had the acid chloride and the carboxylic acid, what did I end up with? Primary alcohol. What do you think I'll end up with this one? Primary alcohol again. One, 2 carbons. 1, 2 carbons. So lithium aluminum hydride, this is your final one it does this with, turns a carboxylic acid, an acid chloride, and an ester all to a primary alcohol. So it doesn't matter what you start with, you'll always end up with the primary alcohol. What about Grignard? How many carbon groups will it add? 2, and then the carbonyl will end up becoming a alcohol. All right, and our final reaction ever in organic chemistry. Amides can undergo one of these. Now this one I'll tell you is a little bit different. So carboxylic acid, acid chloride, and esters with lithium aluminum hydride turn into what? Primary alcohol. But this one's a little different. So what do you think this will turn into? A primary, not secondary, it's primary. What's on here? Not a ketone. Amine. You have your 1, 2 carbons. 1, 2 carbons, keep your amine. So that's the one that's a little bit different. But out of all of those, you're always turning them into a primary something or another. Most of them are an alcohol. Amide happens to turn into an amine. Yeah, you want to know the leaving group? The leaving group, well, in this case, is always going to be HOCH3. So that's a leaving group. It's not, well, it's not really, it's a consequence of lithium aluminum hydride, but yeah. Huh? Yeah. I'm just looking for, I mean, that's a leaving group, but I'm looking, can you get that part there? All right, so those are all of the reactions. So acid chloride, ester, and amide can undergo, additional few reactions that the others cannot. But we've seen these before. Lithium aluminum hydride and Grignard are your strongest ones. They're always going to react twice and create an alcohol. Lithium aluminum with one hydride and copper lithium will only react one time, so you'll keep the carbonyl. When you're naming a carboxylic acid, what does that name end in? Oic acid. Okay, how did you want to review? Did you want to focus more on 2021? Do you want to look at the older stuff? It's mostly new stuff. So there's one question for the cumulative part, one question per chapter. So how many chapters did we have? We had, but not including 20 and 21. 8. So there's 8 old questions. We'll say 9 just in case I'm lying. 8 or 9, okay? And then the rest are new. And there are, I think, 29 questions. So let's say 20 of them are new material, 9 of them are old material. So you will get the chart on the exam. And because I gave it to you on the first exam, I'm not going to also make you memorize it now. So with mass spec, what is that used for? Molecular weight. And how do you know if I have, I'm going to make up, which one would I go to? The tallest one where? To the far right. So do you see this is my last grouping to the right? And I'm going to pick the tallest one, which would be right here. Now, whatever that number would be, say 180, then that would be the mass. So it's always find the last grouping of peaks to the far right, and it's the tallest one there. With bromine, yeah, bromine has 2 peaks at the end at the same height, so it will look pretty much like that at the end. Maybe some little peaks in here. But you would have 2 peaks pretty much at the same height. So if you were doing this and, it had all these other things in here, you would go to the last group to the right, and then you'd be looking at this, and you're like, okay, well, which one is taller? It's hard to tell. Well, that probably means you have a bromine. And the first one's always a little bit taller. Chlorine is a 3-to-1. Something like that. So you might have like these little peaks in here, but you would have 2 higher peaks than the rest of them around it at approximately 3-to-1 ratio. So this is bromine. That is chlorine. And that's pretty much everything with mass spec. IR, how do we do IR? What does that look like? No, that one's NMR. Yeah. This one we have like this, and then we might have something like that. And yeah, 1500 over. Let's say that's 1500 over. That's the fingerprint region. That's pretty much most of your single bonds, except your hydrogens. Let's say this one is at 1700. What would that be? Carbonyl. And then what would this broad thing over here be? Alcohol. And let's just say that these are some just carbon-hydrogen peaks. So what functional group would you see here? The carbonyl with an alcohol is a carboxylic acid. So you look at this, a double bond, so this is a C double bond O. A regular double bond comes in about 1650, and it's usually not as big. In fact, it almost never is as big. So the carbonyl peak is really easy to see. It's at 1700, anywhere it goes almost all the way to the bottom. But a double bond, let's say the bottom of the graph is down here. So carbonyl would have gone, we just put it in, almost like that. Okay, it would have been really long. But a double bond might only be this long, might be even a little shorter, might even be about right there. But you'll see something at around 1650. And like your fingerprint region, it's like it's very close to your fingerprint region because that's 1500. But if you see a peak right past your fingerprint region that looks like it's at least medium length, that would be a double bond. And then your alcohol, carbonyl comes in there. What about a triple bond? 21, 22, around in there. So it's right before your CH peak, so right in this region, like here. It's the only thing that comes in there. So if you have a peak like that, and they're usually not very big, but if there's anything there, usually it's your triple bond. So those, a lot of that is just looking at the chart. Look which peaks stand out the most to you, and then compare that to the chart we have, the numbers. And remember, the chart is like approximate. So if this came in at 1660 instead of 1650, that's fine. It's still very close. And so this would be multiple choice. So let's say, you know, I had all these choices. Let's take that away. I'm going to look at, you know, a lot of naming choices. I'm going to look at the one that has a double bond and an alcohol in it, right, in the name. An alcohol will end in what? Will the name? It'll end in O, but what, like, how do you name it? All? OL? And then a alkene, how do you say that? Ene? Yeah. So it's an ene all. Okay, so just look at the names, and then from the names. So the big thing with multiple choice is to really work it out like you don't have choices usually. Okay? So if I had this graph, I would look at it, I would see, okay, what stands out to me is alcohol and a double bond. Okay? Then I would look at my choices at that point. I mean, I can't go beyond that. But then I would, you know, look at all of them, and the one that has, first I look for alcohol, just look at the ones that end in OL, okay? That might eliminate almost all of them. And then from there I look at, okay, what has all in there plus ene, and then that would be the choice, okay? So go through, I mean, logically, you know, work these out is a thing, and don't do these too fast either. Don't just look at it and be like, oh, I know, and then circle something, and then you end up missing it. So make sure you read the whole entire question, and you really feel like you understand it before you work them out. Okay, and then NMR. So we did shifts. So let's say we have something like this. First of all, how many signals would you get? How many? 4. This CH2 has a chlorine on it. There's no other CH2 with a chlorine. This CH2 is how far from the chlorine? 1 away. This one is 2 away, and that's a CH3. So just the fact that these are further away from the chlorine means they're different signals. Now, this chlorine was, symmetrical somewhere else in the structure, then it might be different. But when they're different lengths away, then they're different signals. So we have A, B, C, D. Out of all of these, which one we shifted the most? D, because it's connected to an electronegative atom. So it's more downfilled. Which one shifted the least? A. Not only is it further away from the chlorine, it also has more hydrogens. Okay, now let's also look at how they could be split. So let's go ahead and draw in the hidden hydrogens. So this one has how many? 3. Here? 2. This one? 2. And 2. Now what's the rule? Neighboring plus 1. So if we look at A, what is a neighboring? B. So 2 plus 1 would be 3. So A is split, I'll put split right here, into 3. B is neighboring what? Yeah, A and C, right? It's connected to both. A has how many? 3. C has 2, so it's 5. Plus 1 would be 6. What is C neighboring? 4. 2 here, 2 there. So 4 plus 1 would give me 5. And then finally D is next to 2. So it would give me 3. Okay, now if I had an NMR, let's say, something like this, okay? I don't have numbers in here. Let's say this is 1, 2, 3, 4, 5. I don't know. Which one is, we don't have no idea what the structure is. I'm just making something up, okay? But which one would be probably connected to an electronegative atom? 5, the one furthest down there. Okay, now we're trying to decide what these are. So remember, I would give you, like, no, not 5. Let's say that's 3 hydrogens in that signal. That's 1, and that's 2. This probably doesn't work out at all. I'm just making things up right now. Okay, so what does this 3 tell me? This signal is what? A CH3. This with 1 tells me it's a CH, and then 2, CH2. So CH2, a CH, and a CH3. Okay? But what does the splitting tell me? What it's next to. And I don't do neighboring plus 1. I do, yeah, so let's say splits minus 1 if you want. So this one is next to 2. So it would be next to like maybe a stage 2. This one is next to 0. It's either next to a carbon or an OH or something. It's next to something with no hydrogens. And then this one has 4, so it's next to 3. 1, 2, 3, 4, 5. Yeah, sorry. So it's next to 4, so maybe 2 CH2s or something. Anyway, so this doesn't work out at all. But that's how you look at it. You're going to look at, okay, where is probably the electronegative atom? And it's going to be the one shifted the most. And then you look at how many hydrogens in each signal. That tells you what that signal actually stands for. And the splits tell you what it's next to. Now with multiple choice, you will have choices. So you can compare things, you know, I mean, let's say these are our 2 choices, and I have some sort of NMR graph, okay? Could I tell the difference between these 2 here? So let's look at it. How many signals would you have here? It's symmetric. Do you see that this side looks the same as that side? So those 2 would be the same. A. And then would the 2 CH2s be the same? Yeah. B. And then what about over here? How many signals? There's not a hydrogen coming off. See, 1, 2, and then how are these carbons the same? Yes, methyls coming off the same carbon are the same signal. So we'd have an A, B, and then both of these are C. No, B has 2 methyls coming off of it. A does not. If A had 2 methyls like that, then it would be the same. There's not a hydrogen coming off your carbonyl-carbon. Right? There's hydrogen in NMR, so to create a signal, you have to have a hydrogen. So just looking at this, just looking at the number of signals, can you tell the difference? Yeah, this one you're going to see 2 signals. This one you could see 4, or 3, sorry. So just from that, you didn't even have to go any further. You can tell the difference between them. And let's say if they had the same number of signals, okay? Well, then you could look at the splitting, okay? So maybe the first signal on this one was a triplet, doublet, triplet, okay? But this one was a triplet, triplet, triplet. Well, the one that had 3 triplets, maybe that's the one that matches up, okay? So first thing I would look at to compare would be the number of signals, okay? And usually I give you 4 or 5 choices, so that probably will eliminate all but 2. And 2 of them I probably have the same number of signals. So then from there you look at the splitting, and you see, okay, which one does the splitting match up with? And then that will give you the answer. Does that make sense? So go in that order. Go signals, then splitting. All right, let's take a break, and then we will review some more. Yeah, we'll look at that. So what I would do, so amino acids are on the exam. When you're looking at the homework problems and studying, look at the ones you feel like represent the chapter the best. You know, if I'm only choosing one out of all of those, you know, which one do you feel like really, you know, represents the chapter? So if I have, I can't think of one. I don't know. But, you know, think about if you could summarize that chapter in one sentence, what would you say? And then find the problem that represents that the best. And that's probably the one I chose. Now, if there's about 2 or 3 of them that could possibly be, then go ahead and obviously work out those 2 or 3. But that can kind of limit it down a little bit. So you're asking about ortho, para, directors, and meta. What part of it are you having trouble with? Deciding what type of director it is, or actually directing something, or? Oh, okay. Okay. What will this put on benzene first? SO3H. Okay. Now that we remember, now we need to look at our directors. NO2, nitrogen's connected. Is it connected to something more electronegative? Yes, so that makes it a meta. Carbon, is it connected to something more electronegative? No, so that makes it orthopara. Something that's meta, is that a deactivator or activator? Deactivator, so it's, I think, MD, meta deactivator. Orthopara then would be activator. Now, which would be more reactive, a deactivator or an activator? Activator. So anytime you have an orthopara activator, that will decide where the next branch will go. So that would be the methyl. So methyl's an orthopara director. So para is how far away? 1, 4. So if we look 1, 4, there's something already there. So can we put anything there? No. So then we look ortho, which would be right here and right here. Does it matter which one? No, they would be the same. So you could put it on either side. So my SO3H is directed by this methyl. So your directors are already on benzene. SO3H doesn't do any directing at all. That's what you're putting on there. Okay? So these, one of these two will direct what you're trying to put on there. It's an activator because it's an electron donating group. All orthopara activators are electron donating, so it's donating electron density into the ring, versus deactivators are electron withdrawing, so they withdraw electron density out. Electron density, so anytime we make a reaction or form a bond, it's with electrons. Okay, that's how you make a bond. So if I'm donating more electron density, that makes it more reactive. If I'm withdrawing it, if I'm trying to take it away, then it's not there, so it's less reactive. So the reason orthopara activators, well, the reason they are activators is because they donate electron density into the ring. And that's based on the difference in electronegativity between, in this case, carbon and hydrogen. The one exception would be halogen. Halogen, orthopara, yeah. It's considered deactivator. It's a weak deactivator, but it's still a deactivator. And the reason there is because, think about if fluorine was on there. Fluorine is a very electronegative, right? So it's actually trying to pull electron density towards itself. All of your halogens are very electronegative, so it will pull electron density out of the ring. So again, orthopara activators are what will direct it. So if we do one, like this. Okay, so between the two branches, which one is your activator? The CH3. Oxygen is more electronegative than sulfur. So CH3, and it's orthopara director. So now I'm going to mark all my orthopara positions. So ortho are both of my 1,2s, and para would be 1,4. Which one for sure would not occur? The one in between the two branches, because it's the most crowded. So I have two possible answers then. What does this put on there? NO2. So this NO2 is at this position here, the left ortho, and then this NO2 is showing at the para. I would say this one's probably a little more favored. The SO3H group, it's a little bit larger than a methyl, so over here is probably a little bit more favored. But you don't have to tell me that much. Just know that this one for sure will not be favored. These other two are close enough that either one could work. Yeah, so the electronegativity we already looked at with the orthopara directors and stuff like that. So then after you can put the positions, the next thing you look at is just size, which will be the next driving force. Okay. What other type of questions? Well, the 21, you just need to be able to recognize it. So 20. So how many carbons in the longest chain here? 4, which would be named not L. Oic acid. Benzene? What? How do we know this is an oic acid? So we make sure everybody knows. The carboxylic acid. How do we name this branch here? What is that? A methyl. 1, 2, 3. And then this is a hydroxy. So which one would come first? Hydroxy, so it'd have 2 hydroxy, 3 methyl. Oxidase, and you have just a different, usually that would be a ketone. So if that was a ketone instead of an alcohol, like a carbonyl instead of an alcohol, then that would be oxo. So alcohol is hydroxy, a carbonyl would be oxo. And they actually name a ketone and an aldehyde as a branch the same. They're both oxo, except if it was a ketone, you would say like 2-oxo. The other one, a aldehyde, you'll recognize it because it'll always be at the end. So this would be the dominant one, so it would have been 1, 2, 3, 4-oxo in this case. Any other questions? When you're looking over or doing the homework and stuff this weekend, let me know if you get stuck on anything. You know, I can only help you if you ask. So don't be afraid to ask. I won't judge you too hard. Yeah. Look what they try to put. No. No, sometimes I will send the email out to everybody, but don't worry, I won't embarrass you. The only reason I do that, if I do, is because I've already had like 5 emails about it. So I go ahead and just send one of the answers out to everybody. So if you see that, it's not because I'm trying to single you out. It's because a lot of people have already asked about it. So I'm just, you know, trying to use my time wisely. So if you remember, like topics covered would be NMR, mass spec, IR. So that was kind of all chapter 1. Exam 2 was over how to make alcohols, how to react alcohols, and then epoxides and ethers. What's an epoxide? The 3-member ring with oxygen. And then what's an ether? ROR. And then the alcohol is OH. The next exam we did was over ketone, aldehydes, and amines. So what's a ketone? Carbonyl with what coming off? 2 R groups. Aldehyde has a hydrogen, so carbonyl with a hydrogen. And what's an amine? Yeah, like a N, we'll say NR3. And R can stand for, in this case, carbons or hydrogens. And then the new material, carboxylic acids, what's that? C-1OH. And then we also did acid chlorides, which is a carbonyl chlorine. Anhydrides, carbonyl, O-carbonyl, ester, yeah, carbonyl OR, amide, yeah, carbonylamine, and that's all of them. So those are the topics we covered. And if you go back and start reviewing, you'll notice that a lot of the reactions were used in different chapters. So, you know, for example, we just did the one here. What is this? Oxidizing agent. What will that oxidize this oxygen to? Carboxylic acid. Make sure you count your carbons. 1, 2, 3. 1, 2, 3. Okay, because we're not adding carbons here, right? We're just adding oxygens. What did I start with? Alcohol. So do you think this reaction was probably in the alcohol chapter? Yes. So you'll notice that, and then what did I end up with? Carboxylic acid. So it's also in the carboxylic acid chapter. So a lot of these you'll notice repeat themselves, okay? Because you'll realize, okay, you know, when we did this in chapter 11, you know, I'm just looking at reactions of alcohols. Now when I'm looking at chapter 20, I'm looking at different ways to make a carboxylic acid, and that just happens to be one. So a lot of these, if you think, oh, there's a lot of repeat, there is in a lot of these. You know, and then like the Grignards, we did with a carbonyl, we did that in the alcohol chapter, because a Grignard, when you react it with like an ester, you make an alcohol. We also did it, I believe, in the ketone chapter. So anyway, so you'll see a lot of overlap in there. I think I actually have the tester here. (24) multiple choice. For workout. 1 extra credit. Extra credit has to do with amino acids. Every amino acid, yeah. Categorize them by group. Yeah. List all intermolecular forces for 2 points. Yeah. People, I would get nothing on that one. So I'm looking on here, 1 through 10 are new material, so 2021. That's 1 through 10, multiple choice. Um, 11 through 21 is old material. So there's 10 problems there. And then 22 through 24 are not carboxylic acid, amino acids. 22 through 24. And then 25 through 28, it looks like, are new material workout. And then your extra credit. And it looks like, because probably how I made it, yeah. They go in order of chapter. So, for example, you know, like number 11 starts the old material. Number 11 goes over chapter 12. And then the next one goes over chapter 13, which is the NMR. And then the next one goes over something with alcohols. Okay, so it follows the order that we did. So that kind of can help you too. Sometimes when you know that, you know the next one, I'm going to do something with alcohols. So if you kind of even know the order of the chapters, that would help you too. So if you know, okay, well, the next chapter coming up is my ketone aldehyde chapter. Well, then probably somewhere in the answer, somewhere, there's going to be a ketone or aldehyde. So. So there's one, just so you know, for the workout, one synthesis, one predictive product, two mechanisms. Any other questions? I don't remember percentage-wise, but it's 150 points. So I think it might be... If you go to 0, though. It might be like 16, 17% of the grade, around there. No, but it would put me in a better mood if you did, instead of trying to figure it out. So in a way, yes.
On the extra credit question, you threw in more information of the extra credit. Is that extra credit? Like you asked what they were. And,
You put everything.
Yeah.
I'll tell you right now, the extra credit deals with a grouping. So I'll ask you, name all the amino acids in the polar group, or the aromatic group, or the non-polar group. Anyway, so that it has to do with one of those. It's one per correct answer.
Let me draw them out.
I'll give you a smiley face.
Yeah, just a smiley face.
Yeah. So probably everybody's hoping for the non-polar group, because that's the largest one by far, I believe. The non-essential? That would be a lot of points. That would be your 20 points. Oh, for the testing thing? Yeah, if you did that, I'll put that on there.
Yeah. Yeah. Yeah, I did just to get it. Yeah, I did it to get it up and yeah.
All right. So I guess just study everything again. Remember, look at the main points of that chapter. And if you had a lot of reactions in that chapter, look at the reactions we focused on more, and maybe reactions that came up later. Then I would say those are probably more important. So if it's a reaction that you only saw in that chapter and then never saw it again, it probably wasn't as important as a reaction that you saw a few other times. Does that make sense, kind of what to study? Everything, yeah. Let's see, today is Thursday. The exam is Monday, so Thursday, Friday, Saturday, Sunday. If you just focus, so every day study chapter 20 and 21, because that's probably the majority of the exam. So every day study that. But then choose, like today, work out the homework problems for exam 1. Okay? And then tomorrow, work out the exam problems for exam 2. And then do exam 3, then exam 4. So by the time Sunday comes around, you'll have them all worked out, or at least one time. And you'll always have 20 and 21. Yeah. All right, and then some of the questions you probably don't need to focus on, and you could probably usually tell those, hopefully. All right, any last minute question? Okay. All right, so we'll meet back here at 9 o'clock to do the presentations. You also will be doing the national exam today, just so you know. Surprise. So make sure you have a Scantron for that. And that's only 20 minutes, so be prepared for that one. We'll do the presentations first. The same one we've taken.
So that exam had open 1 and 2 in it.
Yeah.